All right, so here we have constant velocity problems, and so it's a direct application of what we've been looking at, and these take place in 2 dimensions. So we have a battleship is located at this position, and then after 5 minutes it's at this position. Part A says determine the parametric equations of the boat. So for a parametric equation, we need an initial point, and then we need the direction vector. So if we're going to find the vector from here to here, like think about it as this is point A, this is point B, so the direction vector AB is the coordinates of B take the coordinates of A. So we'll have 6 take 1 gives us 5, and we'll have minus 16 take 4 gives us minus 20. Okay, so an appropriate way to describe it then is it begins at 1,4 plus the parameter time t, and then multiplied by the direction vector. Now I want to point something out. This vector is how far it moves in 5 minutes. So we can really easily account for how far it moves in 1 minute by dividing this by 5. Okay, that's how far it moves in 5 minutes. Like if it moves across 5 spaces in 5 minutes, that means it moves across 1 space in 1 minute. And if it moves down 20 spaces in 5 minutes, that means it moves down 4 spaces in 1 minute. So this is a really good way. That's the vector equation, but to state it as a parametric equation with its position, the x value is 1 plus t, and the y value is 4 take away 4t. And this will describe its position for any value of t, where t is time in minutes. Okay, part B says plot the path of the battleship on the Cartesian plane. So what we're going to do is we're going to find out firstly what is its position when time is 0, when time is 2, when time is 4, and when time is 5. What is its position? Okay, so when we put 0 where the t is, the initial position is 1,4. When time is 2, 1 plus 2t, 1 plus 2 will be 3, and 4 take away 8 will be minus 4. When time is 4, we'll have 5, and 4 take 12, 4 take 16. And here we'll have 6 and minus 16, which is where it is after 5 minutes. And plot, if we're to plot those on the Cartesian plane, we'll just do so very primitively. So to begin with, we're across 1 up 4, and then so 1, 2, 3, 4, 5, 6. That's going to give me enough on the x. And then if we go 4, 0, 4, 8, 12, 16. Alright, so we've got so that's 1, 2, 4, 5, 6, cross 3 down 4, cross 5 down to 12, cross 6 down to 16. So that's its position there, right? That's the path it's following. This is the initial position, and then this is where it finishes. X, Y, coordinates. T is our parameter for time. Okay. All right, find the speed of the battleship given each grid unit is equal to 1 kilometre. Okay, so we've answered part A here. This is part B here. So let's do C. So speed is just distance on time. All right, and what we have, if we think about this vector here, it's moved across 1 and up 4. Let's find the modulus of that, the distance of that. It's going to be the square root of 1 squared plus 4 squared, and it does that in 1 minute. We'll just keep it in grid units per minute for now. So this gives us what, root 17. So that means it moves root 17 grid units per minute, and we're told each grid unit is 1 kilometre. So root 17 kilometers per minute. Okay, so it's not an SI unit, but it doesn't matter, it just says find a description of the speed. Okay, when does the battleship cross the x-axis? So it's not asking for where, it's asking for when, all right? It's going to cross the x-axis around about here. When does that occur? Okay, so it's going to cross the x-axis when the y value is 0, all right? So we can think about that like that. Crosses x-axis when the y component is 0, so that means 4 take 4t is 0, so we get 4 is 4t, we get t is 1. After 1 minute, it crosses the x-axis. And then if we're to determine the angle that the ship makes with the x-axis, we can use the techniques we learned in the previous exercise, or we can just try simplify it. We know that it's going across 1, down 4, okay, across 1, down 4. So what's this angle that it makes with the x-axis? Well, that has a magnitude of 4, that has a magnitude of 1. So we're just doing inverse tan O on A. All right, I can go into that in more detail if you want. Here's the hypotenuse, adjacent, opposite. We've got the adjacent and the opposite side. So tan of theta is O on A, and then the inverse tan to get the angle. 1.3